Alright, let's look at this problem. G of x equals negative 2 times x minus 5 squared plus 3. As you can see, I've labeled the transformations for you already. We have a shift up, we're going to have a vertical stretch and a reflection across the x-axis, and moving it to the right 5. Now, if we were doing this by physically moving the graph, you would probably have to do maybe 4, maybe a little less, but probably about 3 or 4 versions of this graph, just so you can see every transformation and how it affects it. And especially that stretch. That stretch will kind of get you. So let's go ahead and reorganize all the transformations according to whether they're affecting the y's or they're affecting the x's. The 3 and the negative 2 clearly affect the y's, and the minus 5 is affecting the x's. The big clue here is, where is that defining characteristic at, which is the squared, right? Whatever happens before you hit that defining characteristic is affecting the x's. Everything after that affects the y's. Reorganizing it, I would get g of x minus 3 divided by 2. And the other side wouldn't change. So, what would I have to do to the y values from the parent function to get to g of x? Well, let's just simply set them equal to each other, because this tells me what I would have to do to the y values of g of x to get to the y values of p of x. So if I want to know the other way, I'm going to solve like we did before, which would give me, oops, that should be a negative 2. Negative 2 times the y values of the parent function plus 3. And if I did that to them, I would get the y values of the function g of x. On the other side, what would I have to do to the x values of the parent function to get to the x values of g of x? Setting them equal, solving, I would simply have to add 5 to all my x values, and that would take me to the x values of g of x. Now, let's actually do it. Let's take it to the actual table, and let's see what this graph is going to look like. Let's start with the table first. These give you a guideline for what you're going to have to do to the parent function table. And if you follow them, it will apply all your transformations for you right off the bat. No other steps needed. So in this case, I knew that I needed to take the parent functions, my x sub p's, and I needed to add 5 to them. That would give me 3, 4, 5, 6, and 7. On the bottom, I needed to take all my y values, or my range from my p of x, and I needed to subtract 2, or multiply by negative 2, and then add 3, which would give me values of negative 5, 1, 3, 1, and 5. Now, how do we check our answer? Well, you can use a graphing calculator to do it if you want, or you can simply graph it and remember what our transformations were. We're going to the right 5, up 3, and it has to be flipped, and it has to be stretched. So, why don't we go ahead and graph it? Alright, let's graph this thing. So, plotting my points, over 3, up 4, over 3, down 5, 4, up 1, 5, 3. The other side will mirror that. And if you look at your function, you can clearly see it has been shifted to the right 5, moved up 3. The stretch has made it narrower, and it has been reflected or flipped over. And there you have it. This is how you apply transformations to the table so that you can graph. All the transformation and all the previous work is done before you get to the plotting of the points. And if you did it correctly, when you plot your table at the very end, you'll have it done. This does require that you do know what the parent function is, but it should work for basically every parent function, every family there are out there. With the exception of polynomials, once you get into higher degrees, they can get a little bit hairier. We'll deal with that in a different section. But for most families, this will work. Alright, let's look at this example. Here we have a generic function f of x. And here I have the function g of x. G of x is given by taking f of x, multiplying it by -2, adding 4 to it, and on top of that, taking the x's and dividing them by 2 and then plus 1. Here you can see there are a bunch of transformations going on. As a function, it's really hard to actually do this because you don't know what f of x is actually saying. You don't know what the characteristics are. But in transformation terms, it's fairly clear. This is a reflection across the x. This is a vertical stretch. This is a horizontal stretch. This is a shift to the left 1, and this is a shift up 4. Now, you could pick this graph up and try to move it around and do that, but let's apply the method I just showed you. Here is the function f of x. Here's the table values for it. So our question is, what do I have to do to the domain and the range of f of x so that I can get g of x? Well, let's go back and apply what we just learned about transforming the tables. Let's reorganize it, organize the transformations by who they're affecting. We know that these two affect the range, and everything inside the parentheses will be affecting the domain. Therefore, we would get for the range this. For the domain, like before, it doesn't change. So then the question really is, what do I have to do to f of x, the domain or the range of the original function, to get to g of x? Well, we know if I had the table for g of x and I subtracted 4 from it and then divided by -2, I would get back to the original function f of x. Therefore, rewriting it or solving it in terms of f of x, I would then get -2 times f of x plus 4, and that's what I would have to do to f of x to get to g of x. So we've now handled the range for the original function f of x. What about the domain? X sub f represents the domain of f of x. We know that if I had the domain for g of x and I cut it in half and then added 1 to it, I would get back to the original function domain for f of x. Rewriting it and solving, you would get the rule for transforming the domain of the function f of x into the domain of the function of g of x. Using these two as my guidelines, I can now take the table of f of x, which is the only one I have, and I can create the table for g of x. So, this tells me that I need to take all of my f's, all of my numbers in my range, multiply them by -2, and then add 4. On top, I will take all of my numbers in my domain. I will first subtract 1, then I will multiply them all by 2. This would give me the table for g of x. I'm going to walk through one and then I'm just going to give you the rest. So, -3 minus 1 is -4 times 2 is -8. on the bottom. Negative 2 times negative 1 is positive 2 plus 4 is 6. And so following my transformations, I can clearly get my table for g of x. The nice thing is I've handled all my stretches, I've handled all my reflections, and I've handled all my shifts. The easiest way to go back or go about recognizing this is to basically graph it. Let's graph it and see if it happens the way it's supposed to. It has to be reflected, it has to be shifted left, it has to be shifted up, and it has to be stretched both by x and by y. So let's see. At negative 8, I go up 6. And as you can see from my graph, it has clearly been reflected and it has clearly been stretched horizontally. You can see how each piece has also been stretched vertically. And there you go. You now have the graph of g of x. Without having to go through and apply every transformation individually, you have just gone through and transformed the table itself. So hopefully this was helpful. Please let us know if there's anything else you would like to see. Maybe even if you want to see more examples, we'll see if we can't put some more of those up for you. Thanks for watching, and remember, you can find more of our content at 3mathguys.com.